Okay, calculus, here's our second example of implicit differentiation. We are going to find dy dx given this particular curve, and we're going to do this using implicit differentiation because our y's are embedded inside of our function, so they're all mixed together with the x's. So this is what we're going to do. And remember, every time you take the derivative of a variable term, you're going to have to chase that with the derivative of that particular variable with respect to x, because our final goal is always to get dy dx right here. Okay? So we're going to start here. This gives me 12y dy dx. And I'm going to be a little tricky here. I'm going to say minus 4, and then I'm going to use a bracket. And with the x and the y, I'm going to perform the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. All of that is going to get multiplied by that negative 4. So the first is x. The derivative of the second with respect to x is dy dx, plus the second is y, and the derivative of the first with respect to x, I know you're going to say it's 1, but it's dx dx, and that's the end of my product rule. Plus, now I need the derivative of x squared with respect to x, so that's just 2x. And I'm going to ask you to write dx dx because you just took the derivative of a term. So regardless of what variable it was, I want you to chase it with the derivative of that variable with respect to x is equal to, and once again I have a constant on the end, so that derivative is 0. Be careful, people like to just copy that constant, and that is where an error is made often. So we're going to go through and we're going to clean this up. So I have 12y dy dx. I'm going to distribute not just the 4 but the negative 4. That gives me negative 4x dy dx. And then the negative 4 times the positive y dx dx is just negative 4y, because the dx dx is really 1. And then plus 2x, dx dx again is 1, equals 0. You don't have to put the slash to the 0, I don't even know why I did it. So I'm going to get my dy dx terms on one side of the equation, I'm going to get everything else on the other. So I have 12y dy dx minus 4x dy dx is equal to, and I'm going to add 4y to both sides of the equation, I'll get 4y. I'll subtract 2x from both sides of the equation and get minus 2x. At this point, I'm going to factor out my dy dx from both of these terms. I'm going to use a big set of parentheses because there are no other parentheses. 12y minus 4x, and that's 4y minus 2x is just copied. I'm going to need a little bit of space here. I have two more things I want to write down. I have dy dx is 4y minus 2x, all divided by whatever dy dx was being multiplied by, 12y minus 4x. And now I'm going to simplify everything down by a 2, and I'm going to get dy dx equals 2y minus x over 6y minus 2x. That is an equation that will yield the slope of the tangent line for any xy coordinate point that happens to be on the original function. And I have a point that was on the original function. It would be 3, 2. So I'm looking at the tangent line, the equation of the tangent line at 3, 2. First thing I need, since I already have my what? This is the point of tangency. I need my slope. So my slope is given as 2y minus x divided by 6y minus 2x. This can often get very messy right there. So I'm going to ask that you put a set of parentheses down for every variable that you're getting ready to substitute for. Go back into your x first. The x is a 3. Find where it goes and put it down everywhere an x goes. Pick up your 2 and do that. That would be a little bit helpful. The slope is now 4 minus 3 divided by 12 minus 6. 4 minus 3 is 1. 12 minus 6 is 6. That gives me a slope of 1/6. I now can finish this up. Y minus y1 equals m times x minus x1. This is known as point slope form. So I have y minus, my slope is 1/6, x minus, and now my point was 3, 2, and I am finished. You don't need to go any further than that. But for a while, all I'm gonna have to drill you on is trying to get that dy dx. Okay, so good luck with today's work, and I'll see you when I return. Talent out.